Okay, so let's do a 1 minute intro and then we can get started.
Awesome. So hi, Antali. My name is Nilesh. Uh, I'm a software engineer at a startup based out of Palo Alto, and yeah, I have 3 years of experience. I've been working on mostly backend and infra side. So yeah, that's about me.
Okay, cool. All right, so right now it's 6:03, so we'll go until 6:53 my time.
Hmm.
Okay, so the first problem I don't have like it pasted, but I'll just let you know. So you have a 3 by 3 grid
Hmm.
of numbers, and the sum of all the cells adds up to 9. And so numbers can be anything, but the sum adds up to 9. So numbers can be 0 to 9. And our goal is to distribute these numbers so that every cell has a count of 1. And then basically the only operation we can do, so operation is move one number from one cell up, down, left, or right to another. And this costs 1. And then you just want to return the min cost to have 1 everywhere. So just to give you a quick example, so let's say we have like 0, 0, 0, 2, 2, 2, and 1, 1, 1. So this would give you a cost of 3 because you would take 1 from each of the 2s and you would move it up.
Hmm.
And then another example is if it's all 1s already, then this would be a cost of 0. And then maybe another example is if you have like 1, 1, 1, then you have like a 0 here, a 2 here, 1 here, 2. Yeah, let's see. 2, okay, 1, 1. So this would be a cost of 3
3.
because you'd move the 2 up and then the other 2 would go across. So you can
Hmm.
move things however way you want, but basically this is what it would look like.
Hmm.
Yeah. Okay, and you can get started. Let me know if you have any questions.
Awesome. Hmm. Let me start. Yes. So I have a 3 into 3 grid. It's okay. It's always necessary that they are going to sum to 9. So it's
Yes.
always going to be there. Okay. And the numbers can be only 0 to 9.
Mm-hmm.
We want basically to make all the cells to 1 and with them minimum cost. And we can move 1 from a cell to the 4 adjacent cells. And that has cost of 1. Okay.
Mm-hmm.
So let's take this first example. I have triple zeros, triple twos, and triple ones. So if I move this one here, this one here, then we have 3. Okay, 3 cost. See, and let's take this example. So this 2 can go here, and this from this to 1 can go here, then here.
Mm-hmm.
Okay. Hmm. Okay. One more thing that can happen here is this 2 can go here, but then from this 2 it will have to go 1, 2, 3, and 4,
Mm-hmm.
or 1, 2, 3, and 4. Okay, so there are two possible options, 3 and 5, and we want the minimum cost here. Let's see. Okay, let me just think for a bit.
Sure.
If all of them are 1, the cost is 0. So we only touch the cells which have. Okay, it's only 3 into 3 grid. Oh, I see. Okay.
Mhm.
The grid size is fixed. So, okay. We want to find the minimum cost. Okay, so the one thought that I have is what I'm going to do is basically I'm just gonna traverse the whole matrix.
Mhm.
So let's say if I come here at this point, I'm going to basically perform, let's say, a BFS. I will perform a BFS and find the nearest cell which has greater than value 1, which has some value which is greater than 1. So I'll reach here. So I'll take 1 from here. So I'll decrement this to 1 and make this 1. Then I'll come here and I'll do same for it. I'll basically find the nearest for that. And this is the nearest. So I'll make this 1 and this 1. So I'll just go one by one to all the cells and basically from there perform BFS and find the nearest cell which has a greater than 1 value and then basically take a value from there.
So you're
And
saying for every cell that has a 0, you're going to do a BFS, and then the closest one to it, you will use that?
yes.
So I don't necessarily think that works for everything. Like, if you have like this case, I mean, I'm very confident there's like cases where there might be a tie or a cell might be closer, but it's significantly worse to take that. Like actually in this example, I think, um, like for example for this, if you were to take the bottom one, like the bottom one is technically the same distance as the right one, but the bottom one would be better. But if you take the right one, it would be bad. Right? So I don't think you can just BFS and find the closest because that one might screw up other ones.
Yeah.
Does that make sense? Like I can always
Yes.
rearrange it in a way where you can't just take the
Yes.
closest.
Yes. So okay. Hmm. Okay, that makes sense. Oh, I need a way to minimize it. I see.
Mm-hmm.
Okay, this approach would work in this, but okay, but I agree that there may be some.
Well,
Yeah.
I mean, in here, like, what's the closest? Like, they're both the same, right? So how would it work?
Yes. No, so in this case, it would work like this. For example, since we are going iterating through the whole matrix,
Mm-hmm.
so we'll first reach here. So it's gonna take, like.
Oh, I see. Yeah, but I can write it. But I can basically write the reverse of this, right? Where if you iterate through the top, like if there's a 0 here, and there's like a
Yeah,
2
I agree with
here,
that.
and then you see my point, right? So
Yes, I see that point.
something
Yes.
like that. So,
Yes.
okay. So,
Okay.
are there any other things we could do?
Okay. Yeah, just give me a second. I'll just think for one more minute. Oh, okay. I think the other approach is just going to be like, for example, I'm at 2.
Mm-hmm.
So I'll start with all the positions which have from the cells which have value greater than 1,
Okay.
and I'm gonna start distributing from there.
Mm-hmm.
For example, if I'm here, then I'm gonna distribute it right here. Okay, let me think.
So, how are you going to distribute in that case?
I'm gonna distribute it. 4 directionally. I mean, whatever I get in the 4 directions. For example, if this is the case, no, this is the case. Let's say this is the case. Yeah. So for this too, I'm gonna distribute it here. I'm basically gonna check 4 directions. Whichever direction has a 0 value, I'm
But
going
what
to
if they
distribute.
don't? Like, what if there's gaps and stuff, right? Like, there could be like a 2 here and a 0 here,
Yes.
and things like this. So it might not necessarily be right next to it, and also kind of the reverse. Just because it's the closest doesn't mean it's going to be the best. Like, it'll
Mhm.
be the best for that one, but that might screw up the rest. So is there any way we can kind of like do something else where we, you know, I mean, so for one thing, you noted it's only a 3x3 grid, right? So is there any way we can kind of like figure out like systematically what's the best without just saying like we'll just take a cell and we'll just give it to the closest one and like hopefully that works out, because it might not. Like, there's going to be edge cases there.
Yeah, I get your point. Yes.
Hmm.
So, okay, let me just rethink about this problem that we had here. There's 2 here and 2 here and 0 and 0.
Hmm.
Okay, just give me a minute. I'm just think. So, this 2, okay, this 2, this. So, okay, so the problem is for this too, I have to decide whether I want to think about this. But I have to decide whether I have to give one to
Right.
this 0 or this 0.
And you can't necessarily pick the
Yeah.
closest one because it might
Yeah.
screw up other stuff. Yeah.
Yes. I can try all possible ways and then find the least.
Okay, and how would that look like?
Okay, so that yeah. So from this two, the value either can go here or can go here.
Mm-hmm.
To I mean, okay, from any possible cell which have a value greater than 1,
Mm-hmm.
we can try all possible other cells which are 0.
Mm-hmm.
And this we can do recursively then. So what I'm saying is, for example, if I'm at this position, I'm gonna try this as well as this. Okay. And
Mm-hmm.
now recursively, if I try this, now I'll check for another position. I mean, if this still has some value, then I'm again gonna uh, check until the value becomes 1, and then I'm gonna move to the next cell which has a value of greater than 1.
Mm-hmm.
And then from that I'm then gonna do the same from that cell as well.
Okay, and how would you, like, let's say you start this middle one and you want to try to go like left. So how would you go, like, here and then like try the other cell as well
Yes.
recursively? So you want to try like the left and the top.
Oh, so okay, this is gonna play like okay. I think it's pretty simple. I think we can just, for example, if I'm at this position, I can iterate the whole matrix
Mm-hmm.
and see. Okay, this is my first position where I have a 0 value. Let me give some value here and
Mm-hmm.
mark this as visited.
Mm-hmm.
And then iteratively, I will just since that is visited, I'm gonna search for another, which is gonna be in another function, the the nested function call. If you're getting it.
Yeah, but how do we
Uh,
essentially like, so you're saying like you'll go to a 0, you'll find a 0, and then when you find a 0, you'll just find a cell that has bigger than 1 and you like put the number there? Is that what you're saying?
Okay. Let me just think. I think this is much more complicated approach. I think there should be a simpler approach than this.
What do you mean? So what part of it's complicated?
Yeah, the recursive call part of it.
Okay. Well, basically you're trying to try like all possible combinations, right?
Yes.
So is there a way we can do that in like a not I mean recursively, but like, like do you know any algorithms that can like try all possible combinations? Essentially? Like
Hmm.
basically what we want to do is we want to say like let's say we go to this 2 and we're like, okay, we'll try doing this. And then we'll go down that path. But then we also want to do this and then go down this path as well. So is there a way to like is there an algorithm that does that?
I know how we can do this. I don't remember the exact term for that.
Sure. Okay. Sure. Okay, so if you're pretty confident that you know how to do it, we can code it or you can talk about it more. Up to you.
Okay, yeah, I would like to write the thought and
Sure.
then move on to writing it.
Sure.
So, so the idea is basically to iterate through the whole. Okay, this is in a recursive function. Will iterate through the whole matrix, and then at a cell which has a value greater than 1. Now, from that cell, we are basically gonna yes. So we are basically gonna again iterate through the whole matrix, and at a cell which has a value of 0, put a value of 1, and then basically yes, and then basically recurse. And once we come out of this recursion, we are just gonna revert this value back to 0. The cell which was basically changed from 0 to 1 will make it back to 0, and the current cells value will also be back to the what was the actual value here. And this we will do in recursion. And yeah, in the end, the condition at which we basically know that all of them are filled, all of them has 1. We're basically in the recursive function, we are basically gonna have we're gonna check, okay, if all the values are 1, then basically compare it with some global minimum.
Yep. Okay, so this makes sense to me. So what do you think the time complexity here is going to be?
Yes, so time complexity for this. So what we are doing here is we are first basically in every function call we are iterating through the whole matrix, and then again, okay, and then this, how deep then this recursive function can be. So this recursive function can be as deep as 9 length. I think this should be 9 into n square. Why 9 to n square? Because sorry, 9 to n square, because at every function call we are just iterating to the whole matrix, and at max this can be 9 length deep, or you can say 10 length deep. So this should be the the time complexity for this.
Okay, so we're iterating through the whole matrix, and then it can be 9 deep.
Yes.
Okay, so I mean, you basically have to count up all the branches that you can go down. I'm not sure that's correct, but this is also one that's like kind of hard to calculate. So we'll say this is fine. You can double check it later.
No, actually, no. It's gonna be 9 to the power n square. Actually.
Yeah, I think that sounds
Yeah.
more correct to me.
Yeah.
Well, actually, 9 to the power of n squared. So this would be 9 to the 9 or something. It wouldn't be
Yeah.
like 9 to the 80. It definitely wouldn't be that.
9 to the power 80, yeah, something like this. Yes.
I think that's way too big. I definitely don't think, because 9 to the power 80 is like 10 and 10 and like 80 zeros.
This is actually the worst case. Why worst case? Because let's say we have this 9, only one 9 here, and rest all of them are 0.
Mm-hmm.
Then it's basically gonna try every,
So I
For
think
example,
that would be like, 9 factorial, to be honest, because basically like the first slot you have 9, like 9 slots you can put it in, and then after you put in the first one you have 8, and then 7 and 6 and so on. So it's more like 9 factorial times whatever your grid thing is. So I think it's like 9 factorial times like n squared. Not 9 to the, because 9 to the power 80 is like way too big. So I think it would be, because basically you want to think about like at every choice, at every place, how many choices do you have, right? So if you have 9 and all zeros in the first spot, you can put like this, like you have 8 places you can put you can put the 1 in, right? Does that make sense?
yes. Yeah.
And then after you put in 8, then you have 7, then you have 6, and you have whatever. So that would be like 8 factorial plus your grid traversal. So that would be like, basically something like that. But you could double check that in your own time. I think that should be. This is also a complicated time. All right, so I want to make sure you don't run out of time. So let's just get to coding.
Awesome. So what do you want? We want minimum cost. So I'll just say int minimum cost, and then we have a matrix.
And we're at 22 minutes right now, just so I can so you're aware of time.
Yes. So yes, and I think we just have a matrix with us, and I'll just say int n equals to 3. Now we want to write a recursive function for this. Okay. So what I'll do is I'll do void recurse, and then so this is a recursive function that I'm writing, and I will just say we have a global min.
Sure.
And then first we'll check if all of them are 1 or not. So for that, what I'm gonna say is int check is 6 all 1.
Yeah, and it's fine if you traverse this thing like too many times because it's only 9. So just get a working solution. Okay.
Okay, I don't think I need this, but so okay, now we know if and we also need a current cost. What is a current cost?
Okay.
And if all of them are 1, that is true, then basically what we are going to do is we are basically gonna do global minimum is equals to minimum of global min comma current cost, and then we're just going to return it from here. Now once we have this, now we want to basically try all the possible cells. Okay, I'm just gonna copy it from here. Now what we're gonna do is we basically gonna iterate to the whole matrix.
Mm-hmm.
Okay, and then basically find a value. Find a position where it has a non-zero value, greater than 1 value actually. Okay. So what I'm gonna do is I'm saying this. Okay, now basically we want to and then we basically also want to fill some value from there. Okay. Okay, no problem. I'll just write it here.
Sure. Yeah.
Okay, less than 3. There's a bit change in the plan. Basically, what I'm doing is I'm basically iterating through the whole matrix, finding a position where
Mhm.
we have a value greater than 1, and then I'm also again iterating to find some value which is 0.
Yep, I got it. You can keep going.
And then we are once here, and then what I'm gonna do is I'm just gonna do it like this. K of L is equals to 0.
Mhm.
Then for that position, yes, so we are gonna make this as plus, okay, this as 1, and then we are gonna recurse with this vector. And okay, we also have to, okay, let me also do other stuff. I'll just make back to 0.
Mhm.
And also revert this back.
Okay.
And I also have to incur for the cost. Now to find the cost, so I have to find the cost from here to here. And how
Mhm.
do we get that cost? So let me think. If I'm here, okay, so it's gonna be 1 plus 1. Okay, and here, okay, so it's gonna be the the what was that, absolute value of I minus k plus absolute value of j minus l
Mhm.
is equals to like this, and then we're basically recursing it. We'll call it from here vec, and okay, and its current cost would be 0. And and we also want a global cost. So for that global cost, what I'm gonna do is star and star. Okay, this is a thought. Let me dry run through this quickly.
Sure.
So the idea is we have this global minimum and we have this matrix,
Mhm.
and then we're basically recursing through the whole thing, and then finally returning it. I've passed this pointer for global minimum here. Now what happens is we basically first check if all of them are 1 or not, and
Mhm.
if if all of them are not 1, we just basically simply break from it. We can also break from here, but for now I'll just keep it simple, and then I can later on add more conditions here to break it faster. So if all of them are 1, we basically return, and before returning we basically check if the current cost is minimum, then
Mhm.
the global minimum, and then we basically fix the global minimum based on that. Now we are basically iterating through the whole matrix, finding a position or cell which has a value greater than 1, using that value, and then basically iterating again through the whole matrix, and basically checking some value which is 0, making it 1, incrementing the current cost, and then performing recurse again, and then basically reverting the values back. Now to this value would again become to 0, and the current cost would be again come back, and go on like this. So yeah, I think this is a thought. Yes.
Yep, makes sense. Let's try to run it through a test case, see if we get errors.
Awesome. So yeah, I'll say minimum cost, and I just need a vector here. Let's say we will take this one, 110 1 comma 1 comma 0 comma 0 to 1 0 to 1 and then 2 1 1. The answer should be 3. Awesome.
Okay.
So let's yeah, the answer is 3 for this.
Okay, great.
Let
Maybe
me
you can
try
try
it.
like one more example, then I think we're pretty good here.
Yeah, 000 222. The answer should be in this case as well 3
Mhm.
3.
Okay.
Yeah,
Yeah, I think we can move on. Just we only have 20 minutes left, so let's do the second question.
oh, okay, let's move on. Yes.
So I'm gonna paste it. All right.
Okay, so the question is, given an array of CPU tasks, each labeled from letter A to Z and number n, each CPU interval can be idle or allow the completion of one task. Task can be completed in any order, but there is a constraint. There has to be a gap of at least 10 intervals between two tasks with the same label. Return the minimum number of CPU intervals required to complete all the tasks. Okay, so okay, let's take this example. We have 3 A's and just take 20 minutes. 3 A's and 3 B's. Okay, so we first take A, then B, then we take idle, and then A, because there at least has to be gap of 2. And this total takes 1, 2, 3, 4, 5, 6, 7, and 8. Okay, now let's take this example. AC, AB, DB. Okay. Okay, since this is 1, we can basically do it in one go. And then in this case, we have 3 A's and 3 B's. Okay, and the gap needs to be 3. So we do A and then we do B. And okay, 1 2 and 3, gap of 3, so then comes A and then B. Okay, and this would take 3 4 5 6 7 8 9 10. Okay, the number of different tasks can be A to Z. What's the constraint for n?
It can be really, or actually, so I mean, let's just make it pretty reasonable. Let's make it just like, let me think about it. I think let's make it like 1,000 or something. I mean, I honestly, the number doesn't really matter. Just try to
Okay.
have a generic solution.
Okay, cool.
Sure.
Hmm. Okay, let me just think for a bit and mm, okay, so the first thought that I have is each task can occur multiple times.
Mhm.
So we can basically, yes, so we can basically sort them based on the number of times they are occurring.
Mhm.
So let's take this first example. So A is occurring 3 times and B is occurring 3 times. And then we can basically pick the task which is occurring the maximum number of times at that moment.
Mhm.
And then we can also maintain another map which basically stores, okay, at uh, how far is the, how uh, how far in the past is the last occurrence of this element of the or this task.
Mhm.
So for example, since A and B have three times, we can basically pick any one of them. Let's pick A, then we have A here.
Mhm.
Then we can pick uh, anything except B, anything except A, so we'll pick B. Now okay, now what do I have? I will again search for anything which is other than A and B. So I don't have anything. So what I will do is I'll again start from the starting. So A is again Okay, let me explain it like this. So A is 3 times and B is 3 times. So I'll pick A and then I'll pick B. Now I have nothing left. So I'll again come to A, but now since we require at least a gap of 2, so I'll put an idle here. And then I can pick A and then I can okay then I'll have B. Now B is two at a 2 distance, which is greater than n, greater than equal to n. So I can again pick B. Then I have nothing left. So I'll again check for A. And at the same time I'll also decrease, the number of occurrences we currently have left. Let
So you are keeping a count, and you're keeping like when's the last time you've seen it or something on another
Yes.
map.
Yes.
Okay, and when you said that you will sort, like the counts change. So are you going to sort every time? Right, like if you pick A, then B has a higher count. So you're basically saying pick the thing with a higher count. So like when you pick
Yes.
something, its count changes.
Yes.
So how would you
Uh,
handle that?
So I'm thinking of using a priority min heap, a
Mm-hmm.
min priority queue, so which basically stores the count and the
Mm-hmm.
element.
Okay.
And basically, what I will have to do is I will basically have to, the topmost element is going to be the one which has the least count. So I'll pop this up, I'll decrement the count and again push it. So which is gonna take login.
So you said you're going to use a min heap.
Yeah.
So do you want to get the one with the min count or the max count?
The Oh wait, okay. So we want, yeah, the max count. Sorry, it's going to be a max heap. Yes, that's the part.
Mm-hmm.
The one with the maximum count, and then again, I'm just gonna pop it and push it again with the count decremented by 1.
So you're going to pop and push. But what if like the top of the heap or the top whatever elements of the heap are you can't use them? How would you access like the later stuff? Like, for
Oh, I thought.
example, if you have like A, B, C, D, E, whatever, a bunch of letters, and like they all have the same count. Like, if you pop A and its count goes down, like
Hmm,
let's say A has like a count of like 26,
hmm.
and like B has a count of like 24 or whatever. Then you pop A, its count goes down. A is still at the top of the heap, and it's unusable. And maybe the top 5 elements at the top of the heap are unusable or something. So how do you handle getting to the one you want?
I think we don't need a max heap in this case. We can also use some. We can basically sort them once and then basically use a queue. So we
Okay.
pop it and then we pop it and push it in the back of it. You know.
So if you pop it and push to the back, what happens if you have a
Yeah.
case like this? Like you have like A like 50, like B1, C1, D1, and then is like a small number like 1. So in this case, you'd probably want to do like A, B, A, C, A, D. So
Yeah.
so they're not always gonna like stay in the same
Yes.
order.
Yeah.
So
I
so
think.
the
I think
heap so the heap you were mentioning makes sense with
hmm.
like I need to have a count, but how can we like get rid of things don't that we can't use and then add them back in later when like they're available? Does that make like can we have some kind of system there? Like we pop from the heap when it's available, but then if it's not, then we like can't use it, and then when it is available again, then we like add back to the heap, like something like that. Does that
Yes.
make sense?
Yeah, I get your point. So, okay, what I'm going to do is I'm going to use 2 heaps. One is going to be my main heap and one is going to be my temporary heap.
Okay.
So the idea is basically I'll just, go through the whole heap until it becomes empty. And meanwhile, I push it all the elements in a new heap,
Mm-hmm.
something like this. So basically, let's say I'm in a loop. And what I'm going to do is I'm basically going to, uh, I have this heap with me. I'm gonna,
Mm-hmm.
pop until it's empty,
Mm-hmm.
and
So
then
so the first heap is the heap you're like using the tasks. So if you
yeah,
pop until it's empty, once again, like if I have that case where it's like A B A D A C, would that work with what you're saying?
oh, okay. Let me think for a bit.
Mm-hmm.
Someday.
like I think what you're saying makes sense with the, you have the one heap and then your second heap is like the unavailable heap. But so like let's say we use A at time 1, like at whatever index 1. Do we know like when's the next time A can possibly be used?
Once basically all of them are used.
No.
All of the other elements.
No,
No.
because if n is 1, like if you look at this example, right? Example 2, it's like AC, A, B, DB or something. So you don't have to wait till all of them are used. You just have this one, like not the one, but the n. You have to have an n gap between the times you use it. So if I use n in the beginning, then I have to wait like 1.
Yeah, I got it. So we basically can use n number of elements in between the next.
Yeah.
I get your point. Yes.
So if we use A at index 0, then we know like the next time it'll be available is at index 3. So
Yes.
can we use that to like make things unavailable and then make them available again, and then from there pick the best?
Yes.
Okay, and how do we do that?
Okay, so what we can do is, yes, I think what we can do is we can basically make again a heap. But this time I'm gonna store count and the time at which they are available. No.
Yeah, that wouldn't work because you need to
Yes. Okay, let me just think for a bit. And so yes. Okay, so the thought is we are basically gonna pop for pop n times from the heap.
N times.
N plus yeah.
I see.
Plus 1 times.
Okay.
From the heap.
Well, do we need to necessarily pop? I mean, maybe you can, but can't we just pop once? Like, can't we just pop an item, mark it unavailable until whatever, and then we can like pop the next one, mark it unavailable till, and then like have cleanup? Like, do we need to pop a bunch of times in a row? Does that help us in any way? Might make things more complicated too.
Oh, okay.
Like, basically, can we just say like, okay, let's take an item, let's mark it unavailable, and then for the next item, everything that's available, we'll mark it back to available, and then we'll take an item, mark that as unavailable, and then everything that's available, we'll mark it as available, and we can just keep doing that until like we have everything. Maybe because if you pop n plus 1, like you might not even have n plus 1. I mean,
the number of elements that we have, a minimum of that.
I see.
But I get your point.
I mean, that might work as well. So if you think that's easier, so you're saying like if n is 1, we'll just pop 2 because there needs to be a gap of 1, and then we're gonna mark all that as like unavailable, and then we'll keep doing that. I think that seems reasonable.
And if we have less number of elements, then we can just increment the count, the time, and then again in the next iteration. But what you're saying is also, I think that is much easier to think and reason about. So good. Let me just think for a minute and. I think we don't need to pop it. And and we also don't need a min heap.
Okay.
We can just sort it once. Put it in the sorted thing can be like this, It can be, let's say, a vector of a tuple. where the tuple has these three things, the count, the the next time when that is available, and the next time when that is available, and the current element, the element. So we iterate through this, and what we do is we basically iterate through this. Okay, so what I'm saying is, in one at a one at one go, we'll iterate through this for n+1 times.
Okay. And then when you iterate, you will decrement the count and you will update the time.
Update the next time, and then I will again start from the beginning.
Mm-hmm.
And
Okay,
do it.
but how do you keep it in the right order if you just have a vector? If you just update these?
Okay, yes, that's correct. Yes, because there can be a case where, like, the first elements are 50, 10, 20, and the last elements are, let's say, 5, 6, 4, 5, 4, 4. And
Mm-hmm.
after a certain time, we basically want to use them as well. Hmm.
Yeah,
Hmm.
because you might have like a bunch of A's and then like a good amount of B's, but then also a good amount of other stuff. And if you just use A's and B's, uh, then the other stuff you won't be able to like fit and stuff. So yeah. So I guess we don't have that much time left, so let's just talk about it high level. So imagine you have the heap, right, for the thing you were saying with the counts. So if you think about it, if you um well, there's a couple ways you could do this, but
How
if
do you
you
want me to implement this approach? I mean, it's up to
yeah,
you.
yeah.
If you want.
So you can go with this. So if you take this, right, so you pop n+1 times or the min,
Yeah.
then you mark all of those so you get rid of them from the heap, and then what you can do is like, so imagine like I mark something, I use an item at like index 2,
Hmm.
and then I use an item at index 3 and an item at
Hmm.
index 4.
Hmm.
The one that you use first is always going to be available first, right? Because there's like a strict gap of like a constant length.
Yes.
So what one thing you could do is you can just have like a queue of like unavailability, and then you could like throw it on your unavailable queue, and then every time you have like you know what index you're at, and you could just, every time you're at a new index, you just like empty out your unavailable queue appropriately, and then you like pop n+1 items again, and then you put them on the unavailable queue, and then you just keep doing that, and then that way you're always getting the item with the biggest count first. um
But
yeah.
we'll have to push them again from the unavailable queue to the heap, right?
Yes. And I think it'll even be easier to code if you don't even pop the n+1 items, you just do one. So you just pop one item and then you add it to the unavailable queue. And then for the next index, you clear the unavailable queue and then you pop one item and then you add it to the, and so on, right? And then that way, like, I don't think you could do a heap with like counts and next time together. It doesn't really work, but you could separate it out. You could either do two heaps or a heap and a queue. And I think a heap and a queue makes sense because like it's like first in, first out, right? Like the thing that's unavailable first is available first.
Hmm.
So can we do that? Does that make sense?
Yes.
So maybe we could code that. We have a few minutes left, so
Yeah. So what we want is we want the times. So what we are saying is basically we are gonna, yeah, but we are agreeing on this point, right? That we have to again push it back to
yes,
the to
to
the
the
heap.
heap. Yeah.
Yeah. Okay. Cool. So
So you need to maintain the count, and then you need to like pop it off when you use it, and then when it's available again, then you like add it back.
yeah.
Assuming it still has like a count left. If it doesn't have a count left, then you can just like get rid of it.
Yes. This is gonna be a max heap, so it's by default a max heap queue, and this is like the count and the element, and then we basically yes, we basically iterate through this and push it. but I'll need the count first. So what I will do is I'll just map char comma in. Oops.
Okay.
And then we are, let's say, in a while loop. And then what we are doing is we are basically gonna get the minimum of n plus 1 or the number of elements in the, let's say the int 0, the number of elements that we have in the priority queue, which is gonna be n like this. Okay. And then basically, while k and then k minus minus pq dot top and pq dot pop. This is going to be count comma the element itself, and then yeah, we also need a timer here. And then what we're going to do is we basically have this count with us. So, and we need a queue now. So I'll just say queue of tuple. I'll say just queue.
Mm-hmm.
I'll say count minus 1 comma EL. And yeah, and I've done this time plus plus here. And then now, yes, and basically, okay, we don't need this. We can just simply do, or do we need this? For now, I'll just keep it like that. So what we are doing here is we are just basically iterating an infinite loop. We are taking the minimum of this, and then we are basically going through the whole thing and popping from it.
Mm-hmm.
Now what I'm going to do is dot size int this new case after this becomes this, and now we only push to the queue if the count is greater than 1, and then we are basically going to do it like this. So queue dot front is going to be new table.
I see. So you're basically saying like, I'm gonna take n plus 1 items and then I can just clear the queue because like everything can go now.
Yes.
I don't think that works because imagine n is like 1,000. You know, your last couple items aren't available right away, right? Like if n's 1,000 and I push 1,000 items onto the queue, you're basically saying like even if I could have pushed an item on like two iterations ago, and now I'm clearing the whole queue. So I don't think that's what I was saying. I don't think it makes sense to do the. Yeah, I think we can just stop here because we're kind of like a little over time, and then we'll do some feedback.
Yeah.
Okay, so let me just go back. So for the first one, so you restate the problem in your own words, and then you asked about time constraints, and you discussed an approach, but you didn't know that BFS doesn't work. And I pointed out some like edge cases, but then you did figure out eventually like the better approach. So it would have been good if you would have realized that BFS doesn't work, because you could think of the edge case yourself, right? That like I can't just go to the closer one because there's like things that fail. So usually what I do for things like that is I'm like, okay, I think BFS. Can I really quickly think of an edge case? And hopefully you can. I mean, this one's a little bit tough. Maybe it's not intuitive. But then your interviewer would tell you like, oh, but look at this, like it wouldn't work for this or whatever. And so I kind of hinted you in the right direction, and then you figured it out. it did take a little while, and you could have. There's definitely cleaner ways to write it, but it's not a big deal. Like if you do the n by n, it's like 81. What you could have done was you could have had separate like cells for like zeros and then like non-zeros, and then you could store those in like a set or whatever, and then you wouldn't have the like, the n squared. But I mean, because it's only 3 or it's only 9, it's not a big
Yeah,
deal.
yeah.
Then I think your time complexity is a bit off, but time complexity for backtracking is one of the hardest, so I think it's also not the worst. Um, and then yeah, so you basically had a good plan. You had it all working, and then you ran your code very quickly, which was good. Like I'd say for the first one, you took too long planning like what to do. Like you need to get this step faster because we spent like 30 minutes or something or
Yeah.
35 on the first one, and ideally you can do it in like if I give like this one is a little bit harder, but I gave you 50 minutes for two problems instead of 40. So like
Yeah.
so I think it's reasonably doable. So you just got to get to this part like quicker.
Hmm.
Um, yeah, and you basically ideally want to be done at like 25 minutes. So your
Yeah.
coding was good, but basically it's just like time.
Yes.
And I literally did a mock with someone a few days ago where I told them like, hey, you took 45 or 50 minutes, and if this was a real interview, they would just stop. And then he basically said like, oh yeah, so I did the real interview, and then that's basically what happened. Like I was doing well, but I was too slow, and then they just cut me off in the middle of a problem. And it's like,
I
so
agree with that. Yes.
yeah, because they're not going to be like, all right, you're doing good, let's just keep going. So
Hmm.
yeah. So basically on your like out of 5, I'd say your problem solving here was like a 3 because you couldn't figure out like the optimal thing without me hinting. So 3 would be like a weak hire, 4 would be like a solid hire, and 5 would be like super strong hire. I
Yeah.
think your coding was a 4 because you coded everything very quickly. You basically had no mistakes. Um, you could have made your code a little bit cleaner, so that's why I get 4 instead of 5. Like you had this like IJKL whatever thing, and that's where these things kind of spiral into the other, right? Like because you don't have time, you took too long on one. Now the other one kind of suffers because if you had more time, you could have made it better. Um,
Yes. Hmm.
so, and then your communication, I also gave a 4. Honestly, I think your communication is always like very good. Like I can kind of tell what you're doing. I think for some of these plans, it wasn't super clear, so I did probe you a little bit deeper, especially for like the second one. So I'd say for the first problem, this would be like a solid higher. Um, and then for the second one, you resay the problem, and then you didn't ask about edge cases, which you could have. Like, is it only A through Z? Because maybe that could simplify your approach. Maybe you could just do a bunch of sorting because it's only A through like. Actually, no, sorting wouldn't even work. Well, actually, no, sorting would work. Like if you had a number and counts or something, you can just keep sorting over and over, right? Because it's only 26. Like who cares about? So that might have been like one approach. And then you wouldn't even like need a heap. There is like a clever solution where you don't need a heap, you just store it once, but I wouldn't expect you to come up with that. But I did kind of hint you that you need a heap and you need some kind of other data structure to mark unavailability, and I feel like you had a really hard time understanding what that looks like. Like you were really trying to do this like n+1 thing, like pop off n+1, and I just don't think that works. Because yeah, like imagine you pop off 100 items, you have like 98, 99, clear the heap. Well, now if you use this 99 again, there's like you see there's like almost no gap here. So I don't think that works because of that reason. Like maybe it does, maybe I'm not seeing something, but does that make sense?
Yeah. Yeah. Yeah, I agree with that. Yes.
Okay.
Hmm.
And so what I would focus on strongly is like maybe the simple something works, but the thing that would have been a lot easier to code and I would know for sure works, just pop off one item and have the unavailability either heap or queue. Honestly, heap might be easier, but basically you just keep track of like next index available, and then at every index you just clear the unavailable thing. Available heap or queue or whatever you want to use. So like if you say like, oh, I'm using A and it's going to be available at 10, then whenever you get to A, then you can clear out of the unavailability queue or heap, and then you can put it into your available heap. And then what for available, you just always pick the biggest. So you did figure that out. You just always want to pick like the biggest. But I had to point out a lot of edge cases like, well, you can't just have like a queue because you can have like this case. And this was even like given to you in the examples. Like example 2 was that. Also, I think you didn't account for. So if you look in the examples, there's like they tell you there's like idle cycles, right? So if you do that like min n plus 1 length of the heap, you might have a bunch of idle cycles that you're not even like counting. And that's going to get screwed up, right? Like the solution might be like AB idle, idle, like, idle like 100 times or something, and then like AB again. So I don't think your code would have handled that with like the way you were doing things with the time and the K. Does that make sense?
Yeah, I actually agree with that. But I just didn't get one thing, that how will we know that how many type of tasks that we have to use at once? We, we have to use A, B, and C, or we just have to use A and B? How do we know that?
Yeah, so you basically just do like a greedy top to top. So you have a max heap, pop, biggest count. Is that what you're asking? So you can just use one at a time. So you just do this once. So you literally just take the one with the biggest count, mark it unavailable, unavailable, and then for the next thing, you clear up your unavailability queue, and then then you pop off another one. Because you don't get any performance gain by doing like 10 tasks from the heap at once. And I think you get bugs. Does that make sense?
No, my question is, for example,
Uh-huh.
if let's take this example.
Sure.
How do I know? I just have to use A and C.
Oh, it doesn't have to be A and C. It can be A and anything. But like,
Yeah,
yeah.
A and B, just A and B, not A, B, and then again, then not C. I mean, what I'm saying is, why are we in like? Why do we want to do it like this? Like this, not this.
Because if A has a bigger count, like,
Hmm.
so basically, in some cases, it'll be the same. But if A
Okay.
has a bigger count, like if it was like this, then if you did it the third way, like this way, you'd go like A, B, D. And now what you need is like A, and then you can have a B again. So I guess, let's see. So there's A, B, D, and I think, yeah, so this technically works. So let's say you have another A, I guess. So you have one more A. So in this case, what would happen is like now you have one A left over. So you can't do this. So you'd have like idle. So the reason you always want to pick the biggest is because if you pick the biggest, then you'd go like A, B, A, B, A, D, A. And then this would work. And you don't have any idle. So basically you always want to pick the biggest because that reduces the idle thing. Does that make sense? That's why the greedy is the best.
Yeah, I agree with that. So my concern is something else. For example, let's say I have different tasks, each having different counts. What an A, let's say, occurs 50 times. Let's say B occurs 2 times, and these all occur 1 time. So now there's one way that I can do it like this: A, B, C, D, and then A, B, and then A. But we would prefer something like this: A, B, A, C, A, D, A, B, and then A, like this, right? This would the correct answer here.
So you're not asked to get the actual order. You're just asked for like a number of cycles, right?
Yes.
So basically what I'm saying is this bottom one will never perform worse than the top one.
Yes.
It might be equal or better.
Yes.
So that's why you want to do it that. Or sorry. Yeah, that's right. The bottom one will always be equal or better by doing the greedy highest count.
Yes.
You can look at examples. You're never going to find a counterexample of that performing worse.
I agree with that. I agree. This is going to outperform every other option.
Mm-hmm.
But how do we know that I have to stop at B? I don't have to stop. I'm not going to take A, B, and C at a time. I'm just going to take A and B.
Oh,
Yeah,
yeah. Because yeah. So if you have, so this case, right? If you have A, B, C, D, or even this, if I go A, B, C,
yeah,
now I have idle. So you basically look at the examples and you try to see like, can I just take whatever? Can I just do them in order? And you could see like here, this is not good, but this would be good. A, C, what is it? A? Yeah. So you basically just look at the examples and you're trying to find a pattern and you try to see like, oh, I can clearly see that like taking the one with the biggest count always outperforms. And I think example 2 gives that to you. Maybe I deleted it. Or yeah, so you can basically find an example. So that's something you have to come up with the problems. Like I have this and this. Let's say you should be like, okay, with this now I know that like this is better than what I just said. Does that, because basically like if you take something, then it becomes unavailable. And so because you want to finish as fast as you can, you always want to take the thing that occurs the most because you want that to become available as fast as possible because that's the one you need to write the most times. So that should be like an intuitive like problem solving part where it's like, okay, whatever I take is going to be unavailable. That means I want to take the thing with the biggest count because that's the thing I need to write down the most times. And I need to maintain these counts because it's always just going to be the thing that's the biggest count. Maybe that's like not intuitive to you. If that is that what you're saying?
No, that is intuitive,
Uh-huh.
but I'm not able to think from how I'm going to implement that. That is what I'm thinking.
Oh, well, yeah. So you basically just have a heap, right, of item and count,
Yes.
and then whenever you take it, so if you let's say you take it 0 and n is like 1, you know that it's available again at 2, right?
Yes.
So then you just have a heap or a queue. You could use a queue where you store the time and then your letter. And then every index you're at, so you're at some index, you just look at your queue and pop off everything that is available now. So once you get to 2, then you'll see like, oh, I have an A at index 2, so now I can get rid of this and then add it back to my available heap. And then, so basically you just clear your unavailable and then you take the highest count. And you keep doing that until both your unavailable queue and your heap are empty. Or you could use an unavailable heap. Either one's fine. It's going to be the same thing. So does that make sense? And this
Yes,
is like a common, or maybe not common, but there's like a lot of problems like this where you use something, you have to wait like X amount of time, and then you can use it again. And so there's like one way you have to use it, but you have to wait the X amount of time. So you usually have like 2 data structures. One, you're taking the stuff, and then the other one, you're marking it unavailable, and then you're clearing. There's like a problem called like process tasks using servers. There's this one. There's a bunch. You can just like put it into an LLM, like give me some problems with this like type of thing. There is like a really clever solution here, but I wouldn't expect people to come up with it. Where it's like you take your biggest count and you know where it has to go, so it has to be like A and then a space and the A, and then you can basically use some calculations to figure all this stuff out. So it's like I know A has to go like this. Now I have 3 empty slots, and then I put B's in like wherever. But that one for an interview is like pretty unrealistic. But I think the heap and like the unavailable heap is like more obvious. So that's what I would expect is like a pass. So for the second one, because you struggled so hard, I'd say like your problem solving in DSA was like a fail. Your coding was good again, but I'd say the second was a fail. And then basically if this was like a text screen, I'd like do maybe like the lean move forward or whatever. Maybe not. It would be right in the middle. And I think for an onsite, this would be a fail just because you didn't come up with like a valid solution in time.
Yeah. Yeah, that makes sense. Yes.
These are definitely, this is a tougher problem. The first one is also a tougher problem. So I am kind of doing tougher problems, but you've done like 4 mocks, right? So if I just do like some super easy stuff, I don't think it's like super beneficial. Also, I think it's a good idea to do mocks that are harder than the level you're interviewing at, because if you can pass those.
Absolutely, yes.
Okay. All right, well, cool. I have another one right now that I'm like 10 minutes late for, so I will see you later.
Okay, thank you so much, Anatoly.
Okay.
Have a great day.
You
Bye.
too. Bye.